Now, we'll see in this video how the area of a triangle can actually be computed using determinants. The area of a triangle is not a difficult concept. It comes from the area of a rectangle, for example. So if we have that rectangle, we know the area to be the base times the height. And then we know that the area of a triangle would be half of that rectangle, which is, so the base times the height is the area of that big rectangle, and the area of the triangle is just a half of that. What we don't see in geometry is how to compute the area of a triangle if all we know is the endpoints. We don't really go for the endpoints. We go for the length of the sides maybe, or ideally height and base. Of course, any of the sides can be a base. Now, the interesting thing is that the determinant of a 3x3 matrix can actually give us the area, so the area of this triangle. And here's the setup, something very simple. The triangle with corners x1, y1, x2, y2, x3, y3 has area given by a determinant over 2. So actually, this kind of hints to the fact that the determinant really gives us an area of a parallelogram or a rectangle. And here's the actual matrix. So area of triangle is 1/2 of the matrix. So you put the coordinates of the points in the first two, so you put them in the rows with a 1, x2, y2, 1, x3, y3, 1. Now, if one of the points, let's say x3, y3, if x3, y3 happens to be the origin, then the determinant that we get here is really determinant of a 2x2 matrix. So imagine here having 0, 0. Then you can do expansion along the last row where you have a plus sign. So you get the determinant of that smaller matrix. Then the area of the triangle equals 1/2 of the area x1, y1, or determinant x1, y1, x2, y2. So if one of the points, sorry, I wrote that as a matrix, it should be a determinant. So this sort of makes sense. You have a 2x2 matrix. So if you have and the area of a triangle is also sort of two-dimensional, so that's kind of hinting we don't have the ones in the third column. And the interesting thing is, so this picture corresponds to something like this. I need this part. So let's say we are like this. That didn't turn out the way I wanted it. Like that, maybe. It's as good as it's gonna get. So let's say this is 0, 0. Then here you have x1, y1, and here you have x2, y2. Then you get the area of the triangle to just be 1/2 of the determinant that you get by putting the corners the two other endpoints that are not in the origin in this matrix. Now, the interesting thing of how that relates to a general triangle that is not in with one endpoint in the origin. Of course, we can always move triangles to the origin because the area doesn't change by just translation. But let me show you the following thing. So let's say that the origin is actually somewhere inside this triangle. Let's say this is the origin. It still works. This idea will work even if it's not. And then what we do is if we connect the three corners to the origin, we get three subtriangles. All right. Now, if I look at this determinant, 1/2 of the big determinant, x1, y1, 1, x2, y2, 1, x3, y3, 1. Let me do expansion along the last column. So I want to compute this determinant by expanding along the last column. So what do I get? Each term will have a 1/2. Expansion here, so remember, plus, minus, plus. So I have a plus, and then I'll have a minus, and then I'll have a plus, right? Plus, minus, plus. So when I expand here, I have 1 times the determinant x2, y2, x3, y3. So I will write that. x2, y2, x3, y3. Then I will have minus 1/2 of the determinant when I remove this row and this column. So I have x1, y1, x3, y3. And then I have plus 1/2 when I remove, or the cofactor for 3, 3. It will be x1, y1, x2, y2. Now you see each of these submatrices, each of these determinants actually give me one of the areas of these smaller triangles. So x2, y2, here is that point, x3, y3, and then I assume that the third point is 0, so I get that area. So this area corresponds to this part. Then I have x1, y1, which is here, and then I have x3, y3. Why is the minus coming? Because you see, it's a counterclockwise direction. So I go, it has to do with direction, right? I'm going this way, then this way, and then that way. Whereas for the first one, I did x2, then x3, right? This is counterclockwise. This is clockwise, and that comes with the minus sign. And then here I have x1, y1, x2, y2 with the 0. That gives me that area. So what you get here is a linear combination or a sum of areas where you get another point of the triangles that you obtain if you connect with the origin. If the origin is outside, that still works, right? You would have a triangle like that, another triangle here, and then which other edge am I missing? Here. So some areas will be negative, some will be positive, and that's okay. At the end, this will work out. Now, that is all that I want to say for the area of a triangle, but what is interesting is the area of a parallelogram. So if this is the area of a triangle, then this area should somehow be area of a, or rather, if this area is area of a triangle, then what is this area? And that's the area of a parallelogram, right? Because you can always think of triangles as parts in a parallelogram, not just a rectangle. You can think of them as parts in a rectangle, but if you want to work only with the edges, you sort of you see one edge here can give me a parallelogram, right? Two endpoints, x1, y1 and x2, y2, for example, they can define uniquely that parallelogram. So how do we know? What I'm trying to say here is, let's say area of a parallelogram. So let's say we have the following thing here. I'll try to draw it as much as a parallelogram as I possibly can. And maybe, so I don't want it looking like things are horizontal. Okay, I'll give it another try. Be patient with me. So like that maybe, and then like that, and then maybe like that. Make it look a little bit more as a parallelogram. And then let's look at the endpoints. So assuming that this endpoint is 0, 0, and we can always do, because we can always do this, we can always shift these objects, because all we want is the area, and shifting doesn't change the area. Let's say this endpoint is x1, y1, and this endpoint is x2, y2. So I have this interpretation for a triangle. I can double the triangle, and so the area now becomes, so the area x1, y1, x2, y2, because it's doubled now, it's twice the area of the triangle that is over here, right? This triangle would be 1/2 of that area. So if I double it, I get the area of a parallelogram, right? So this is the area of a parallelogram. Where these two edges these two endpoints don't really give me an edge. If I connect them, I get a diagonal of the parallelogram. And then I also have one of the endpoints be at the origin. So I have an area of a parallelogram. How do I know that a parallelogram that's starting, I should say, starting at 0, 0? And this is the segue into defining volumes. So how do I know that this determinant gives me the area of a parallelogram? I could use geometry and try to prove that if I have such a parallelogram, the area is going to be x1, y2 minus x2, y1. But what is more interesting for us is to try to define this area as a determinant, or interpret the area of a parallelogram as area. So you see, as determinant. So area of a parallelogram starting at the origin, so that's important. It's a function. It is a function of the endpoints of the parallelogram. You can think of area as a function, and if you've ever taken Euclidean geometry, that's exactly how the area is defined. It's defined in a very, very similar way as the way we define the determinant through those three properties, 1, 2, 3. And the first property that you will see in defining area in geometry, in Euclidean geometry, would be to define the area of the unit square. So when the matrix A, so let's call this determinant of A. Okay, I want to be able to refer to this x1, y1 as an x2, y2 as a matrix A. So when the matrix A is the identity, what do you get? So if A is the identity, 1, 0, 0, 1, then if you draw this, you have, so in the coordinate plane, here is 0, 0. Then here is 1, 0. and here is 0, 1. So the parallelogram in question is just the unit square, right? We are representing the unit square. So let me write that. The parallelogram is the unit square. What is the area of the unit square? The area is 1. What is the determinant of the identity matrix? It is 1. So the determinant of the identity matrix is 1, and 1 is the area of the unit square. So the first rule that we had about determinants is satisfied by the area, with the interpretation that the matrix A is obtained by putting the endpoints as rows in the matrix. By the way, the same interpretation could be made if we put the rows as columns, because the determinant of A equals the determinant of A transpose. So whether you put x1, y1 as the rows or you put them as the columns, it really doesn't matter. You would get the same answer. Now, what about the second rule? So the second rule for determinants was what happens when rows get exchanged. So if I have this matrix A and I exchange the two rows, what happens? Well, what I get is the same magnitude of the determinant, but the sign has changed. Well, in the interpretation of area is always a positive number. So if we define area to be the absolute value, to be more precise, then it doesn't matter. So the absolute value stays the same. The determinant changes sign, but the absolute value stays the same. The absolute value. And the area, similarly, the area doesn't change just because you decided to list the endpoints in the opposite order. The area is the same. But the sign of the determinant just tells us whether we listed the endpoints, the vertices of the parallelogram in a clockwise or in a counterclockwise order. So we get some information from the sign. Now, rule number 3 had to do with linearity in each row. So if I look at rule number 3, if row 1 is multiplied by t, what happens? So I have the matrix A with components x1, y1, x2, y2. Now, what about this other matrix, which has tx1, ty1, and then x2, y2? What I'm trying to prove here is that the second matrix, let's call it a sub t maybe, that the area that parallelogram represents is t times the previous one. Well, if you have a parallelogram like this, remember one side stays the same. So this over here is 0, 0. This over here is x2, y2. And now x1, y1 is multiplied by some number t. Let's say that's maybe 3, right? It extends, it could shrink, but let's say it extends that one line to tx1, ty1. You understand here that the area of the new parallelogram is t times the previous one. How do you understand that? I mean, the interpretation, if it's 2, if t is 2, what you see is that you're doubling the area, right? So the interpretation of the area for the new parallelogram really matches. We have that the area of the new parallelogram equals the determinant of a sub t, right? So when I stretch one side, that's exactly how much, or when I multiply one side, one edge by a number, I stretch the area in that same way. So linearity, multiplication by a scalar, works perfectly. The other part that we have to show is what happens. So what happens when we add a new row to, say, row 1. So if we start with x1, y1, x2, y2, and then we move to x1 plus x1 prime, y1 plus y1 prime, and then x2, y2, we know that the determinant here needs to add, right? The determinants, maybe I'll write it as a determinant. So this determinant satisfies x1, x2, y1, y2 plus x1 prime, y1 prime, x2, y2. We know that the determinant satisfies this rule. The question is, does the area satisfy this rule as well? Right? This is what we're trying to prove. And if we can prove this, then we show that the area of a parallelogram satisfies the same rules as the determinant, therefore it can be interpreted as a determinant. And the reason to go this difficult way is because then, once we have shown these rules, it actually matches, or it can be extended to higher dimensions. We can talk about volumes, we can talk about volumes in 3 space, 4 space, 5 space, even though we cannot possibly imagine it. So let's draw a picture to represent this addition of x1 prime, y1 prime. I think I can squeeze it in here. So we have a parallelogram that starts at the origin, okay? So here it is, starting at the origin. And then we have the point x1, y1 here, and x2, y2. Now x2, y2 stays unchanged. And then what we do is we add an x1 prime, y1 prime. So we're adding vectors here. The way you add that vector is you add it at x1, y1. So let's say we go here maybe, and then we will add it here just to see what's going on. So we have that new parallelogram. So here we have, we've added x1 prime, x2 prime, y1 prime. So this is x1 plus x1 prime, and then y1 plus y1 prime. And really the new parallelogram that we obtain from adding is the one that we get right here. We get this new parallelogram, which is with the dashed lines, has the area of x1 prime, y1 prime. So that, maybe I'll do it in pink. So that parallelogram matches with the area here with that matrix, and it adds up to the area of the front two parallelograms. So what we see is that it is true that the determinant of the 2 by 2 matrix with components x1, y1, x2, y2 satisfies, the area of the parallelogram that starts at the origin satisfies the three rules for determinant, which means that we can interpret or identify the area of a parallelogram with a determinant. So really, the determinant of a matrix, of a 2 by 2 matrix, gives us an area of a parallelogram that has one of the edges starting at the origin, or one of the vertices at the origin. So we can use this to extend to the 3 by 3 case, and that's where I'll stop here. So imagine we have a box. So let me draw, or try to draw. That's pretty ugly. Okay, so here is one axis. Okay, I think I'll use freehand because I think I'm better. There. So this will be, say, Z, and this will be Y, and this over here will be the x-axis. And now assume I have a box that is not necessarily rectangular, so it's not a rectangular prism, meaning that the edges are not necessarily at right angles. They could be, but they don't have to be. So let's say I have one vertex over here represented by the vector, by one vector, let's say A11, A12, A13. Then let's say I have another vertex represented by the by the point A21, A22, A23, whether I say a point or I say a vector, it's kind of the same thing. And then let's say I have another one represented in this direction. I promise to draw the whole box. You will see it. So this would be A31, A32, A33. You see why, I mean, I could say just x1, y1, z1, x2, y2, z2, x3, y3, z3, but you're getting the point that I'm trying to set up a matrix that will have these 3 points, A11, A12, A13, then A21, A22, A23, A31, A32, A33. So I'm putting the points, and as you can see, the points are sort of placed in the matrix in a counterclockwise direction, or right hand rule if you like. This gives me the volume of the box. Now let me draw that box so you can visualize what's going on. So let's do like that. This is the box. These are sort of the the edges in the 3 different directions of the box. So I have like that. That's the one edge. So if this way, we are seeing half of the box, if you wish. And then you have the other 3 edges. So think of this as sort of the back side. You've cut out 3 sides and you're left with 3 sides of the box. Then here we have now the top. Okay, that's not very parallel. Okay, I hope you can imagine that. So if you take one corner of the box and you place it in the origin, and then just walk up the 3 or along the 3 directions and look at those endpoints. Now, again, the box doesn't have to be rectangular. We don't know whether the edges are meeting at right angles. So, but it is a three-dimensional box. And so if you just look at the three endpoints, and of course they will be sort of given by lines, but if you look at the three endpoints and you put them in a 3x3 matrix, what you will get is the volume of the box. And you can try doing this with, proving this again, but it's an extension of the two-dimensional case into the three-dimensional case. Now, I gotta be honest with you, I will not torture you with volumes on the exam. The reason I did this video was because these things can actually be useful in calculus. And for those of you who are yet to take advanced calculus classes, especially those of you in engineering, this may be something interesting to see.